Hi, and welcome to this session where we'll take a look at the Composite Steel Beam module in the Structural Engineering Library. The first thing that we'll do is start out with a brand new project file, and we'll see how to add a composite steel beam calculation to the project file. So I'll click on the Calculations division and then click the Add button, and from the Beam category I'll come down to the Composite Steel Beam button, give it a click, and now we can see that the Composite Steel Beam module has loaded and is ready to start to receive some input from us. So at this point what we'll do is step through each of the tabs that are shown on the Composite Steel Beam module, work through all of the input thoroughly, and then we'll jump down and we'll take a look at the results that are provided for us for a composite steel beam design. Starting here on the General Data tab, we begin with a description, which could be something meaningful to us for the project, like Beam B1, for instance. The next thing that we see is the analysis method that we want to have used, and this is our choice between either ASD or LRFD methods. For the purposes of our video, I'll stick with the ASD option. The next category down is referred to as stress method. And at this point, what I'd like to point out is that the AISC 360.05 option is the one that follows the 360.05 provisions as closely as possible. The prior method is one that is optional and offered only for legacy files where we were using a slightly different version of stress combination. It generally worked out to be a bit conservative, and so we've optimized things a little bit by introducing this option that more closely follows AISC 360.05. So I'll leave that as the selected option for our video here. The next category is called Design Values, and you can see that it calculates a value for the yield stress of the steel beam. It also calculates the Young's modulus for the beam. It allows us to enter a maximum allowable deflection ratio for both total loads and for live load. And the only change that I'll make here is I'm going to revise my total load deflection ratio to 240. I'll leave 360 as my live load deflection ratio. And we'll see these in action when we start to take a look at results. Now I'll move over to the right hand side of this screen, and we have our composite data area. This is where we're going to define the construction that we want to analyze. And what I have in mind is a total slab thickness of 5 1/4 inches. And I have envisioned that we're going to use a 2-inch metal deck. So what I'm going to do is immediately come over and select the option that indicates that this will be a slab on metal deck construction. Using this icon, I can open up a metal deck database, and I'm just going to come down to my Volcraft 2VLI option, the 2-inch deck, and click Use Selected. What that does is indicates that deck for me, and it populates these rib measurements for me. So I have a 2-inch rib height, I have a 12-inch rib spacing, and then I have opening width at the top and opening width at the bottom, all populated based on the data for Volcraft 2VLI that's built into the program. Just to finish off this right hand side, I do have in mind that this will be a typical beam, so the deck will be perpendicular, but this is where you would indicate whether the deck is oriented perpendicular or parallel to the beam that you're currently designing. Okay, so I'm looking at this as a slab on metal deck. Now I'm going to hop back over to this column, and I'm going to enter a value for the effective width for our beam. We have a little help pop up here that just reminds us of the requirements when selecting or determining the effective width for a composite steel beam according to AISC 360.05. Let's just assume for our purposes that we have an 8-foot effective width on this beam. So we'll enter a value of 8 feet. The next decision is this shored construction or unshored construction? This has an effect on the types of stresses that will be calculated and the results that will be displayed downstream, but most commonly I'll stick with the unshored option and we'll see the unshored results. Next we need to indicate the stud diameter, so we'll choose the 3/4 inch diameter stud from the drop-down list box. Now we come to the section where we need to provide the program with the value of QN, which is the capacity of a single stud. Fortunately, we have this button right here which allows us to use a little pop-up calculator to determine the value of QN with a little bit of input from us. So in accordance with the newer table in AISC 360.05, I'm going to bump the stud tensile strength up to 65 KSI, and then I'll just visit this drop-down list box to indicate that we have a condition where the deck is perpendicular to the beam, and I'm going to assume to begin with that we have the 1 stud per rib condition, so I'll select that one. And now we can see that it calculates or looks up the value for RP for us. It calculates the maximum possible value of QN and reports the final value of QN based on that maximum and the other formula that goes into QN. So we have a value of 17.24 kips per stud. So what I'll do is click Use Calculated QN, and when I do that, we'll see that this 11 kip value will update to 17.24. So there it is. That's our appropriate value of stud capacity for the purposes of our example. Now I'm going to assume that we have a 3 KSI concrete mix for the topping, and I'll use a value of 145 pounds per cubic foot for the weight of the concrete fill. The last section that we have to pay attention to here on the General tab is referred to as partial composite action. This is where we specify exactly how we want the program to consider the composite action to behave when it designs the beam. So the options are that we can specify we want to have full composite action, or we can tell the program that we want it to just calculate the minimum number of studs, or we have a third option at present, which is to say that we want it to use a certain specified percentage of full composite action where we could adjust that value accordingly. So for our example, we'll just come back to the full composite action. And now that's a full look at everything on the General Data tab. So our next step will be to move over to the Beam Span Data tab. The Beam Span Data tab is a fairly simple one for us. We basically do two things on this tab. We establish the span length for the beam, and we establish the steel section that we want to use for the beam. Now I would point out that in previous versions of this module we used to be able to specify multi-span composite steel beams. We've since found that that was very rarely used, and it had some issues with it regarding the way that it was calculating allowable stresses or nominal strengths, design strengths at the points where beams were supported at the interior. And so we've decided to bring the module more in keeping with AISC 360.05 provisions and just make it a simple span composite steel beam module and a single span module at that. So what I have in mind for our example is a 30-foot span. So I'm just going to click on the span length, key in 30, register that value, and now we can see up here on the graphic that we are working with a 30-foot span. And then over here on the right-hand side, what I'd like to do is use a W16 by 31 for the section. There are two basic ways that I can do that. One is that I can use the Quick List tab shown here, select the W section, scroll down to the 16s and pick a W16 by 31. Or the other option is that I can use the full steel section database, where I could come into other editions potentially and take a look at an older section. But what I would do in this case is select the 13th edition from the AISC steel database, W sections, and then either scroll down to the W16s, or I could limit the depth, perhaps like I have done right here, and then quickly pick out the 16 by 31 and click the select button. I would just add that there is an entire video that is dedicated to the use of the steel section database. So although I'm going through this process a little bit quickly, if that's of interest to you, please feel free to take a look at that other video where we go into depth on how you can use the features of the steel section database. So now we can see that we've created the beam as a W16 by 31, and we see that echoed both up here on the beam graphic, and if we just took a peek down at the results section, we'd also see that it's using a 16 by 31. So our work is done here on the beam span data tab. What we'll do next is move on and take a look at the span loads tab. Now here on the span loads tab is where we can assign the loads that we want the program to consider as it designs our composite steel beam. And this is a pretty powerful tab in terms of the loading options that are available, so we'll take our time and step through these options in quite a bit of detail. The first thing that I'd like to point out is that there is an option up here near the top to automatically consider the self-weight of the steel beam. So for our exercise, I will select that option. Notice also that because we've selected or defined a slab, whether that happened to be a solid thickness slab or in our case a slab on metal deck, we've provided a cross-section profile to the computer, and we've also entered the unit weight of concrete. So there's enough information for the program to calculate the slab self-weight for us if we chose to do that. And you can simply do that by checking this option. For our exercise, I'll leave that deselected only because it gives me an excuse down below to show you some other loading features and how those can potentially be used. The next thing that we would do is we would focus on populating this table of loads using the tools that are here just above it. So we can add loads, delete loads, and copy loads. And for each load that's in the table, we can specify whether it is a point load acting at a certain location with a certain magnitude, or if it's a full-length uniformly distributed load, or a partial-length uniformly distributed load, or if it's a trapezoidal load. For our purposes, what we'll do is just assume that we have all uniformly distributed loads, a nice even distribution of load across this beam. I'm going to click, while I have this item in the table selected, I'm going to change it from the none loading type to the uniformly distributed loading type. Now we can see full uniform indicated down here. And that opens up the options here for us to define the load that we want for this particular line item. What I'd like to do is I'd like to demonstrate how to use these controls over here in the load application category, because they are absolutely key to the proper solution for a composite steel beam. And what these address is the sequence of loading, the time stages in which the defined loads will occur. So what I'd like to do is I'd like to start up at the very top, and I'm going to select the tributary width checkbox because I don't want the tributary width to default to 1 foot in this case, but thinking all the way back to our effective width of 8 feet, I would like in this case to define a tributary width that is also equal to 8 feet. This way I can enter unit area loads down here in units of KSF, and they'll automatically be multiplied by my 8-foot tributary width to turn them into line loads. Now what I like to do is I like to think in terms of the sequencing of the application of loads. The first thing in my mind that's going to occur is there's going to be some construction live load on this beam. So I'm going to come over to the load application category, and I'm going to indicate that this load item that we're currently working on is going to define a construction loading condition. Specifically, it'll be a live loading condition, and I'd like to use a 20-pound construction live load for this design. So I'll enter that in units of KSF. That will be 0.020 KSF, or 20 pounds per square foot on this 8-foot tributary width. As soon as I click in another cell or another field, it registers that value, and now we can read this line as it's a full uniformly distributed load with a tributary width of 8 feet, a magnitude of 0.02 KSF applied to the entire length of the beam. And the load application is indicated as non-composite only. In other words, it will only apply to the non-composite checks on this steel beam. This 20 PSF live load will never be considered to apply to the composite section, because by the time the beam becomes composite, this 20 PSF of construction live load, workers, buggies, pumps, hoses, and so on and so forth, will be gone. Okay. The next thing that I'm going to do is come over to the left, and I'm going to say I need to add another load. So I'll click Add. Notice it defaults to the None type. I'm going to again indicate that this is to be a full uniform load. And now what I'm thinking of is the weight of the concrete. I'm going to come up and select the option called Always Applied, or it's also referred to as both pre and post composite loading. Notice that the input boxes here have been narrowed way down so that it can only accept a value of dead load. The only type of load that logically would be applied both pre-composite and post-composite is one that is a dead load. And what I have in mind here is the weight of the wet concrete, and we'll think of it also as the weight of the metal deck combined. So what I'd like to do here is I'd like to again say that I want to use the tributary width of 8 feet, and I'm going to consider a weight of 54 pounds per square foot, or 0.054 kips per square foot, as both a pre and post composite load, one that is applied both to the bare steel beam as well as to the composite section, and that represents the weight of the wet concrete fill on the metal deck as well as the self weight of the metal deck. And when I click in another field, that registers the 54 pounds per square foot on an 8-foot tributary width for the full length of the beam, and it is applied both to the pre-composite checks and the post-composite checks. Okay, we're almost done. The next load that I'd like to add creates a third line in the table, again a uniformly distributed load, still with a tributary width of 8 feet. And what I have in mind here is to define the post-composite load, the load that's applied only after the concrete has cured. Here we have the full range of all of the loading types available to us, but what I have in mind is a live load, an occupancy live load of 80 pounds per square foot, so 0.08 KSF. And then I'm going to assume that there's some superimposed dead load on here as well. It could be a floor topping, it could be some additional mechanical or equipment of well-defined loading, so that I feel comfortable referring to it as dead load. In any case, I'm going to indicate that there's an additional 20 pounds per square foot of dead load that will be applied to the post-composite section only. So this will only be considered to be applied after the concrete is fully cured, meaning that it'll never affect the design of the bare steel beam. It'll only be superimposed on the composite steel beam. So with that, I can see that I've successfully defined a full-length uniformly distributed load of 8-foot tributary width with a magnitude of the equivalent of 20 pounds per square foot of dead load and 80 pounds per square foot of live load. That is a very thorough look at the tools that can be used to define loads on composite steel beams, and with specific focus and emphasis on these controls over here, the load application category, so that the loads are sequenced properly and applied appropriately to either the bare steel beam and or to the composite steel and concrete section. So with that, our last step will be to take a look at the load combinations tab as far as the modeling process goes. The load combinations tab is the location where we'll identify the load combinations that we want the program to consider for the design of the composite steel beam. Notice that over here on the left the tab indicates ASD, and that's because we've chosen the ASD design method way back at the beginning of the video. So the first thing that we might do on the load combinations tab is notice that we currently are basing the calculation on ASCE 705 load combinations, but let's just assume that we want to use the IBC 2009 combinations. So what I'll do is click the Change Load Combination Set button, and then from the pop-up menu I'll choose the IBC 2009 option. Now we can see that we're using IBC 2009 combinations. If for any reason there were certain combinations in the list that we didn't want to run, we could always come in and selectively remove them by clicking the Run checkbox as a toggle. The Run button at the top of this column allows us to quickly mark all, clear all, or invert the selections. And then I would also point out that if there's a specific reason why you would want to modify some of the load factors for this one calculation, you can come over to this little padlock icon and click it so that it appears unlocked. And notice that that changes the appearance of the screen so that you can then come in and you can edit any of these values. Changing values of load combination factors within a calculation like this one does not go back and change the factor in the original database. It only makes a one-time change to the factor right here in this calculation. So you can feel comfortable making any changes that are calculation specific, and they will be retained for the remainder of this calculation, but they won't affect any other calcs based on this template, either prior calculations nor those that will follow based on this template. I don't have anything that I need to change in particular, so I'll just reset the lock back so that the factors can't be changed. I would also point out that over here on the right hand side you have even more control over the load combinations. So if you choose to incorporate the additional vertical component of load in the dead load category as a result of seismic, then you can check this option and enter a value of SDS, and that small additional vertical component will be combined with whatever factor of dead load is currently in the load combination, and that'll happen for all of the combinations that do include some component of seismic. The other thing I would point out is that by default we're running the load combinations just as you see them here, which incorporate the positive form of wind and the positive form of the earthquake loads. But since wind comes and goes, and the same with earthquake, there are times where the loads that you specify, it would be desirable to have them looked at both in the positive and in the negative sense to represent a reversal of that load. Not always true, but sometimes that is the intent. And so these buttons can be used in those cases where you want to create both the positive and the negative load combinations that incorporate wind and or seismic. So that's a pretty thorough look at the load combinations tab. The next thing that we'll do is we will drop down to the bottom portion of the screen, and we'll start by taking a look at the calculations tab, results, specifically the Summary Results tab. The Summary Results tab starts out by providing us with the maximum bending stress ratio that was calculated. It tells us the steel section that we're using for the composite steel beam and the percentage of composite action that's being considered. And then it breaks out the information on the basis of the pre-composite condition and the composite condition, and it indicates the applied moment for each condition and the allowable moment or the design strength, in this case Mn over omega, for both pre-composite and composite conditions. Continuing down, it gives us an indication of the controlling load combination that's producing this maximum bending stress ratio, and then it gives us an indication as to where that maximum bending stress ratio was found to occur. Moving down the page, we have deflection information, so we can see a reading of the maximum downward pre-composite deflection in units of inches, and also because of the potential for upward loads being applied, we have a maximum upward pre-composite deflection reading if there were any upward directed loads. Based on those values, we report a pre-composite deflection ratio, and then we move down into the composite deflections. So we see a maximum downward composite deflection of about 1.28 inches in this case. If there was any upward deflection of the composite section, that would be reported here. And then we have a composite deflection ratio. Moving over to the right, we see the maximum shear stress ratio indicated. And again, a reminder that this is being based on a W16/31. We can see the applied shear stress or shear force in this case. We can see the allowable shear force or the design shear strength. And then we can see the location where that design shear or the maximum shear stress ratio was found to occur. So that's the left support for our span. And then finally we have a note that indicates that if we're interested in maximum support reactions closely related to shears, that we can find those further down in the tabular results. So the next tab that we'll take a look at is the Maximum Combinations tab. On the Maximum Combinations tab, we can see a report on a load condition by load condition basis of the maximum stress ratios for bending and for shear. And then we can see a report of the applied moment and the moment strength, and the applied shear and the shear strength for that particular loading condition. The next tab over is called Studs. The Studs tab is used to report the stud requirements for the current design, and in a situation where we had concentrated loads sprinkled out there on the beam, it would be a little bit more interesting to look at. But because of the fact that we've used all uniformly distributed loads and full length uniformly distributed loads at that, what we end up with for this particular example is not all that exciting, but it just indicates to us that from support number 1, in other words the support at the left hand end of the beam, out to 15 feet, which happens to be the point of maximum moment, the design requires 27 studs, and then for the other half of the beam 27 studs as well. Now, if this was an actual design, this would be a good time for us to take a look at stud count as compared to the number of down flutes that we anticipate over that half of a beam span, and potentially come back and revisit the decision that we made way back here on the General Data tab when we used the stud capacity calculator and we assumed 1 stud per rib. So at this point we might say that we would have approximately 15 down flutes in half of the beam, and we're going to need about 2 studs per rib in some situations. So we might choose to come back and use a more conservative estimate for our stud capacity QN. And of course we would want to take a look at the summary design results here and make sure that everything still worked okay. But just keep in mind, and of course now it's a cat chasing its tail, because as the capacity goes down the number goes up and so on. But just wanted to point out that this is the location where you would need to put some thought into what you're entering up here for a stud capacity and the assumptions that you made in that particular table. I won't follow that through in the interest of just demonstrating the module. I'm just going to leave this as is and not try to resolve that stud count issue, but just make sure that the studs that you see here are consistent with the capacity and the assumptions that you've made back here in determining that capacity. With that said, we'll move on to the next tab, which is referred to as the Moment, Shear, and Deflection Summary tab. On the MVD Summary tab, we start out with a list of many loading conditions for the current design. What I'll do is just expand the dead plus live condition. And now as we move over, we can see at incremental slices all along the length of the member, a value of the pre-composite moment, a value of the construction moment that is removed before the final condition, a value of the post-composite moment, and then a final moment that algebraically sums those values. We can see Mn, the nominal strength of the composite section. Then we have a reference to the code here that indicates whether this is a plastic section or an elastic condition. We see the percentage of composite action that's being considered, the value of omega, and then Mn divided by omega. And then as far as the shear goes, we have a report of the ratio. We can see the applied shear, the value of Vn over omega. And finally, we have a sum of the Qn value for the studs. So that information is provided on an incremental basis all the way along the span for many different loading conditions. The next tab over will be the Deflections tab. On the Deflections tab, we again see a variety of loading conditions that might be of interest for evaluating deflections. And if we expand one of those, we can see that at incremental slices all along the length of the member, we are provided with a report of the pre-composite deflection, and then a value for the construction load deflection. Those are the loads that are removed prior to the composite action. And then we have a value reported for the load that is added or superimposed on the composite section. And then those are algebraically added so that we can arrive at a total or a net deflection for the final condition. And then last, over here in the right-hand column, we have a value for the moment of inertia about the strong axis that's being used to determine these deflections. So that can be evaluated for all of these loading conditions that are provided for us. The next tab is referred to as Reactions. The Reactions tab provides support reactions at the left and at the right for a list of loading conditions that might be of interest. So we could come into the dead plus live condition and take a look at the reaction at the left and at the right, for example. The next tab over is called Properties. The Properties tab is used to provide section property information for a range of shear connections going from 100% all the way down to a lower limit of 25%. So we can see in the leftmost column that we have an indication of the location of the plastic neutral axis. We have an indication of the analysis type for each of those shear connections. We have exact dimensional locations for the plastic neutral axis, the sum of the shear stud capacities and the number of studs on one half of the span, the nominal moment capacity for each of these percentages of full composite action, and then we have a moment of inertia for the steel beam, the transformed section, the lower bound moment of inertia, and then the value called I, constant stiffness. The reference for that, by the way, is provided down here to a section in AISC 360.05, and we've even documented a couple of the assumptions that had to be made in order to produce this value. So that's a look at all of the columns here on the Properties tab. And that actually completes all of the horizontal row of tabs that are offered in the calculations section. So the next thing that we'll do is visit the Sketch tab. The Sketch tab actually has two sub-tabs to it. The first one is called Span and Loads, which shows an elevation view of the beam, indicates the steel section that's being used, the span length that's defined, and then it shows a graphical representation of the loads, which in our case are all full-length uniformly distributed loads where the magnitudes are indicated numerically. The other sub-tab is called Cross-Section, and this takes a look at the section view of the beam. Again, the beam is shown and called out graphically. The full thickness of our slab from the top of steel to the top of slab is defined, and then we can see the effective width that we've defined in the program. So those are the two views here on the Sketch tab. The next thing that we'll do is move down and take a look at the Diagram tab. The Diagram tab allows us to look at diagrams of moment, shear, and deflection. And within each of those options, we can choose to either look at graphs of all load combinations superimposed, or we can deselect that and then come into any particular load condition of interest. So here's a moment diagram specifically for dead plus live. When you're looking at these diagrams, just keep in mind that the vertical dimension is generally fixed. And so if you look at and try to compare a dead plus live with, say, dead, there's no change to the graphical appearance of the diagram. What changes is the meaning of the vertical scale. So when we're looking at dead only, the vertical scale represents 71 foot kips, whereas if we look at dead plus live, it represents almost double that. The same thing holds true when you look at the shear diagrams and the deflection diagrams in terms of the scale. This icon over here to the right offers an enlarged view. It conflicts a little bit with the program that I'm using to record the video, so when I try to get that pop up, I can't actually display it for you. But if you want to take a look at a larger view of the diagram that's currently shown here, you can hover over that icon and take a look at that as well. So that is a complete look now at all of the items in this results panel. The last thing that I'd like to talk about are the options that are up here at the top of the screen for output. Now that we've seen how to configure a composite steel beam calculation, and we've seen all of the output or results values that are provided for us in the lower portion of the screen, I just want to close by reminding you of the options here for documenting your calculation and producing output. So remember that you have an icon here called Properties that allows you to select or deselect certain sections of interest in your report to document your design. And then once you make those selections, you can come over to the Preview icon and take a look at a report preview and make sure that it is what you expected. You can adjust that as you see fit. And then you can either print from the preview or save to PDF from the preview. Or if you need to make changes, you can do that. And then there are icons right here on the toolbar to print directly to PDF or to send it directly to your printer. So that is a very thorough look at the composite steel beam module. I hope that it's been helpful. Thank you very much for your time. Take care and have a great day.